Okay, so okay, welcome to the fourth class. So I posted the YouTube link on the class discussion thing. So let's just review quickly what we did last time. So last time we were looking at this construction of 4 wise independent random variables, and what we did was we said that we will have some finite field f. We want k wise independent random variables, and we would have k has to be less than log f. And what we will get is the size of f many random variables, which will be k wise independent. And the way we will get it is we'll pick k random elements, alpha 0 to alpha k minus 1, uniformly at random from f independently. So that will be our seed. And then whenever, so as I said, there will be size of f many elements. So whenever someone asks for the element labeled by a field element gamma, we just evaluate the corresponding polynomial with the alpha on gamma, and that's our output. And then the claim was that this set of random variables, where you pick the alpha at random, and then this is the gamma random variable, which is the evaluation of the polynomial of alpha on gamma. These set of size of f many random variables are k wise independent, and that's because of the simple fact that essentially because of polynomial interpolation. Basically, there's exactly one polynomial. So if you have k distinct points, then there's exactly one polynomial which takes k values, k even values at those points of degree k minus 1. So with k coefficients. So the point is that there is always one, and there is exactly one. So that's the thing, and that gives us so this claim I didn't prove, but I basically gave you all the things you need to prove it. It's essentially just follows from the fact that the von Neumann matrix has non-zero determinant. So yeah, or you can even prove it explicitly. You can extrapolate any polynomial. You can interpolate any polynomial of degree k minus 1 at k points, k distinct points. So this would be, so what do we have after this? So what we have is that if there is some field f, then we have after all this calculation, we have random variables. The number of random variables is the size of the field, and the random variables take values also in the field, right? I mean, these evaluations are in the field, right? So these are also elements of the field, and we have size of field, many of them, and they are k wise independent. So alpha in fk is chosen. The random variables. So that's gamma. F value. So they take values in k wise independent. Random variables. So let's come back to our application. For our application, what did we need? So we needed signs. So our random variables are supposed to take values in +1, -1, and we needed how many of them? The size, the alphabet size. So D of them, right? Where D was the alphabet size, and we wanted them to be 4 wise independent. So k is equal to 4. The size of the field should be at least D, right? Because we want at least D many random variables, and the value should be in +1, -1. Okay. So what I said earlier is that there is a finite. Yeah. So what are the finite fields we know? So certainly you can see that F2 is a finite field, which is just two elements 0 and 1. So just two elements 0 and 1 with 0 plus, like, I mean, just do arithmetic modulo 2. So that's a field. Similarly, you can convince yourself that for any FP, integers modulo P is a field. So at least for every prime we have a field, and I actually told you that there is a unique finite field for every prime power. So which of these should we choose to get our thing? So remember the random variables here are f value. So random variables are f value, but what we want is +1, -1 value, so or at least 0, 1 value, something which takes two values with equal probability. So what kind of finite fields might we try to choose? So our requirement is D. So is D random variables which are 4 wise independent and which take values in plus minus. So one option would be just to pick a prime bigger than D. At least the arithmetic is easy. It's just arithmetic modulo prime, right? What's the problem with that? So is this fine or not fine?
Like, it's not evident to me what would be the mapping from FP to plus.
Yes. So the question is, how would you take a random element in FP and map it to F2? So yeah, you could do this. You could just say everything from 1 to p minus 1 by 2 is so p will be odd, of course. So f p minus 1 by 2 is on 0 to p minus 1 by 2 is one side. Everything after that is another side. But there is a bias, right? So you can never divide p elements equally into two equal parts because p is odd. So
Maybe
this.
we should take the smallest power of 2, that is greater.
Yeah, so so then the option seems to be that we can do, yeah. So next, so choose D is the smallest. Set that to D equal to D. At least this time uh, there is a uh, there is a map, right? I mean, yeah, half there are even number of elements, half the elements. Somehow we'll decide which half. Half the elements go into one side, the other half go into one side because these are uniformly yeah. So because we want uniform distribution, and what we had about the construction I was giving us k-wise independent uniformly distributed. So each individual random variable is uniformly distributed. So this might, at least in principle, might work. So the question is, how do you do, where do you get hold of f2 to the d? So fp was easy. I will just take integers and compute model of p. Where do you get f2 to the d? So I think most of you must have seen this, right? Or what's so can there be is there be again this can you show hands on this Zoom thing? So everyone who knows how to compute in f2 to the d, or how to, yeah, like how to represent elements in such a way that you can make computations in f2 to the d, should raise their hand in this Zoom. Whatever there's an interface here for raising hand. I think you have to click on something called reactions. Okay, just one person. Okay, so not about okay, that's interesting. Okay, but okay, so yeah, so let's do that in some detail then. Yeah, because it seems so, but yeah. So, okay, so one construction, in some sense, the only construction is the following. So, and I'll just do it for f2 to 3. The same thing works for fp to the d also. So, so yes, so this, let me save this and start further. So yeah, so the construction is actually in hindsight quite natural. So the point is this: so you look at polynomials in f2x. So these are all polynomials with coefficients in f2. And so basically, we'll try to go modulo something, not primes, but something that look like primes. Actually, not quite prime, or something to say, but yeah. So they have one property, they share one important property with the primes, and that's what we are trying to construct now. So yes, we look at the set of all polynomials in F2. So this is like Z. For FP, you had the integers, and somehow you went modulo something. So now we're again go modulo something. So what will go modulo something is what are called irreducible polynomials, and we'll see why that is good, why that is. So okay, so what is an irreducible polynomial? What is an irreducible polynomial in F2 to the x? So a polynomial px in f2x of degree d, just to avoid quibbling, I'll say bigger than 1, is irreducible if there is no, if there are no polynomials gh of degree strictly less than d. Px equals gx. So basically, it cannot be factored into two polynomials of strictly smaller degree. So primes have this property in integers. You cannot factor a prime into two smaller, into integers, both of which are smaller than. So in 9, so yeah, so what's the big deal about irreducible polynomials? So they have the same property as the prime, which is the GCD of an irreducible polynomial to any other polynomial is either the polynomial itself or 1. Okay, so does everyone see that? So so this implies if P in f2x is irreducible, so and q in f2x is such that that px does not divide q2. So divide just means that there's another polynomial, so that qx is px times that one. Does not, so the important thing is now does not divide q x. Then there exists Rx in f2x such that qx times Rx is equal to 1 modulo px, which is the same thing as saying that qx times Rx is equal to 1 plus px times sx for some s x in f2. And this basically says that you can take the set of all elements, so the set of polynomials modulo q forms. So now it's easy to see that this will form a field because you can do inversion. So you just you look at all the polynomials modulo p. Of course, all the polynomials that are divisible by p go to 0, so they don't need an inverse. Every other polynomial, when you take its representative modulo p, has an inverse, which is this r, right? That you get from this. And this the confusion from here to here is goes exactly the same way as you would do it over the integers, using the standard definition of the standard property of the GC, that it's the smallest magnitude linear combination so the GCD of two elements is this sort of the smallest, in some sense, linear combination that you can get of those two elements. So smallest non-zero linear combination that you can get of the two elements. So just the same proof would work here as well. Yeah. So basically, our definition of f to the d is we will define it to be what is written like this. Okay, so this is the same thing as yeah. So I mean, so you see what this is, right? So this is like all qx. So one way of writing this is all qx in f2x, degree of q and less than degree of p. So this includes the zero polynomial, the one polynomial, and all addition, multiplication, everything defined. So addition, of course, doesn't matter, but multiplication, and with addition, yes, addition doesn't matter. Multiplication and inversion. So inversion is like finding an element such that multiplying it by would give you one. Inversion to find modulo. So before anything, let me just ask one question. How many elements does this have? I mean, I already wrote the answer, but why is that answer correct? So degree of p is d. How many polynomials are there of degree at most d minus 1 over f2?
So every
sorry.
Yeah, so each so you just have to decide the coefficient of
Yes,
each
and there are d
extra
coefficients because it's degree d minus 1. There are d coefficients, so 2 to the d.
2 to the.
Okay, so this is one definition, but the crucial fact that everyone won't prove is that all fields are, yeah. So there's a theorem that you won't prove that there's only all other so all fields. Yeah, I don't know how to. Yeah, so there's only one field. Yes, okay. So all they're both right, but I just not sound it. So there is only one. Exactly one. So basically, all the different constructions that you might get by using different irreducible polynomials will be isomorphic. But this is not needed for us. For us, all this needed is that have a way of computing. We have a way of computing with f2 to the d, provided we need one more piece of information to do this, right? What? And what is that?
Access to this.
Yes, as soon as we have access to this polynomial p, then we are done. Right? So okay, so let's see if we can find some irreducible polynomials. Can someone give me a irreducible polynomial over f2 of degree 2? First, let's see, of degree 1. Can you give me an irreducible polynomial of degree 1 over f2?
X.
Huh?
X.
Yeah. Can you give me an example of a polynomial of degree 1 over f2 that is not irreducible?
No, like, because you can't reduce it to get degree. Like,
Yeah, so
just
degree 1
constants.
polynomials are by definition irreducible. I mean, yeah, that's nothing you do. Can you now give me an example? Yeah, so x is a irreducible polynomial of degree 1. In fact, every polynomial of degree 1 over f2 is irreducible, or any field is irreducible. What about degree 2? So can you give me an example of a degree 2 polynomial that is irreducible over f2? Or maybe even if it helps over real numbers, can you give me a polynomial of degree 2 over real numbers that is irreducible?
The first thing that came to mind is x square plus 1, but in that is like in mod in f2, like
Okay,
wouldn't
so
that be just x square minus
let's
1?
take example. So let's say example. So one example is that x square plus 1 is irreducible in Rx. And why is that? Because if it were reducible, it would have to factor into linear factors, and therefore it will have to have real roots. But we know that x square plus 1 does not have real roots. That's one way of seeing it. Okay, but it's not irreducible over the complex numbers, right? Because the way the factorization is exactly the same roots, right? These are not there. Okay, good. But is it also? It's also not reducible. It's also not irreducible in f2 to the f2x. And why is that?
Because this is just x square minus 1 f2.
Yeah, so the point is that x square plus 1 is equal to x plus 1 into x plus 1, which is x plus 1 square in f2. Why is that? Because it's just x square plus 2x plus 1, but 2 is 0 in f2.
Yeah.
So this is not in f2. Yeah. Okay, so this is not there. So what other polynomial of degree 2 is left?
1 plus x square.
X square.
Yeah, x
Plus
square. But x square is also so x square is also reducible, right? Because x square is just x times x. Right? So that doesn't work. So not irreducible.
x square plus x plus 1.
Yeah, so that's what I think Shubda was also saying. So but let's try one more. X square plus x. This is also not because it is x plus x plus 1. Yeah, so what Shubda was saying earlier and is that x square plus x plus 1. And this is irreducible. And the simplest way to check it is to just try all possible factors, right? I mean, how many linear factors are there? Like there is x plus 1, that there are just two of them, and you can check by dividing with both of them that this leaves a remainder. So it has no factors of size 1, no of degree 1, and therefore it has to be reducible because it's of degree 2. Of course, there a polynomial of degree 3 could be reducible. Well, that also will work. A polynomial of degree 4 could be reducible even though it has no factors of degree 1. But for degree 2, we are just to check with factors of degree 1 and we are done. So irreducible by brute force. Yeah, so check that x does not divide px, and neither does x plus 1. Okay. Okay, so at least we have found it is a polynomial of degree 2. And again, I will not say, but there exists so another theorem. In fact, you can even count all these things, like how many there are and so on. You can write expression for them. So there is an irreducible polynomial I mean, not just one, there are many, and so there exist. Then there can be many. There is a polynomial px of every degree. So all the f2 to the d we can get by this method. Okay. Good. Yeah, in fact, these two theorems are related, sort of. I mean, in the sense that given such a field, you can show that you will find a polynomial. Yeah, but let's not go there. Okay, so there are reducible polynomials, and so using one of these reducible polynomials, somehow we will. So for our application, so coming back to our application. We will choose just once, right? So this is the point that this will just done once. It's not like you have to do it at every step for one, like, and you can even do it just once, like once in your lifetime, and then always use that one for one, which is actually what people do. So like if you look at library implementation of these things, especially for small degrees, they will have just chosen one nice irreducible polynomial and just use that. Because all of them, none of them is going to give you any special properties except for one thing. So we'll see what that one thing is. So we'll choose once. We will choose just for once an irreducible polynomial of degree d, which is like log base 2, at least this much, right? And use the k-wise independence construction. Over f2 d using this. So now each element of f2 to the d is just a polynomial of degree d, which we will interpret as a polynomial of degree of t. So it is given by exactly d bits, right? Because each bit is a coefficient. So each such polynomial. So each element is now represented as the coefficient bit vector of dimension small d of a degree d minus 1. So but now, even now, we will get this as our random variables are not f2 valued, they are f2 to the d valued. So they will be d bit vectors. How do we get a bit out of them? We needed a plus one minus one.
Can like take parity.
So yes, we can use anything, in fact, because the factor, yeah, so independent. So yes, one way of seeing it, you get 4 ways independent d length bit vectors, each of which has a uniform distribution. And taking a function of 4 wise independent vectors will not drop the 4 wise independent. So we just take some function. All you need to keep track of is that it should have the uniform distribution. So this is uniform distribution over 0, 1 to the d. And we can do anything. Just take one of the coefficients, or if, because it's uniform, that will also be uniform, or take parity as one was saying. So any of those works. And yeah, so to get a bit, to make them UAR bits, take parity or a fixed index. Okay. So all of this is fine. And now after all this, yeah, so with all this, what do we get? So now for each So remember we had these SK things, right? So one second.
Question.
Yeah.
The size of the field is not exactly capital D, right? It could be more than capital D.
Yeah, yeah, but we have more random variables. You can just ignore some of them. That's fine.
Yeah, but then how is it that the first bit is uniform?
No, so the bit is fine, right? So there are two things the field size is being used for. One is that it's a uniform distribution. So okay, so let's just look at this. So here, right? So do you see this? So we have we have size of field many random variables, each of whom is uniformly distributed over the field.
Yeah.
So,
okay. Thanks.
So I just so basically I will not run the algorithm on some of the indices, but whichever indices I run them on, they are still uniformly distributed. Yeah, so that's a good point. Yeah, so there are two things this field size is being used for. One is for how many random variables can you generate. The other is what is the space. So somehow, yeah, so it's a bit unfortunate that these two things are the same, are represented the same object. But what is happening is that there are some s random variables, each of whom is distributed over a set of size t. It just so happens each of whom is distributed uniformly over a set t. It just so happens in our constraint that s and t are equal, but it need not have to be. So all we are doing is we'll, instead of taking all the s random variables, we'll take a subset of them. Okay. So yeah. So in our application, so yes, I'll write this down in the notes also. So in our application, so notice that we had this the number of counters was s times k. So basically we had these rows, right? So yeah. So we had this. So each yi, so there is yij, where each yij was this sum over fl. Fl is a frequency of the lth element times ulij, and our constraint was that for a fixed ij pair, this d random variables uls must be four-wise independent signs, uniform signs, four-wise independent uniform signs. So in our setting, that means now that we can do this with order log d, so small d, which was order log of capital D, many bits. So for each row of this ulij, we need that many. And how many pairs ij were there? That we had was like s times k. So that was 1 over epsilon square times log 1 over delta many counters. And for each row, we needed now instead of d, we just need log d. So our final okay. So yes, maybe yeah. So before that, I'll just write the remark that the point that Sagat raised. So note that d can be less than however while so the construction gives us two to the d uniformly random four-wise independent signs. We just drop 2 to the d. We just ignore it. So that's Yeah. So yes, and what I was saying is that now, so we had sk, which was O of 1 over epsilon square log 1 over delta counters. The randomness needed for each of which we needed a vector of d 4 y's independent uniformly random signs. So okay. So now, yeah. So now the question is how many? Yeah. So what does the construction tell us? How many? What is the number of bits we need for each of these vectors? So we need to store the 4 alphas, right? So the construction requires you to take a random polynomial of degree 4 over the field. The field is of size 2 to the d. So each element requires d bits to represent, and you need 4 of them. So the total requirement is 4d, is 4 times small d, which is 4 times log. So for each counter, we need to store this alpha in f2 to the d4 chosen independently. It's because the vectors, the crucial thing was that the vectors for different counters were independent. So there we can't save much. For each counter, we just have to choose this one guy in f2 to the d to the 4, which require chosen independently. So this requires how much storage? This requires 4 times d, which is 4 times log d, which is order of log d storage per counter. So now we have that the total randomness storage is sk times order of log d, which is order of log d log 1 over delta. Remember, epsilon was the accuracy parameter, what delta was the probability parameter. Okay, but is this the only storage we have? We also have to store the counters, and each counter can grow how much? Each counter can, so there are, if we see n elements in total, each counter will grow, will need log n bits, right? So if we see a total of n elements, each counter needs only order log n bits. So, we get total storage of order 1 epsilon square log 1 over delta. So this is just the number of counters, and for each counter, the counter itself takes log n, and the randomness takes log t. So, so yeah, so the crucial thing is no linear growth in D as we needed, right? Okay, but when any element comes, a single element comes to you, how many operations do you have to do? So this is the storage cost. Now we also have to worry about the computation cost, right? Per update. So for each new element, you have to go and update all the counters, right? So each of the SK counters have to be updated. And they have to be updated using this pseudo-random bit. This bit itself requires some computation because you have this random polynomial, you have this identity of this element, and using the identity of the element, you map it into this 2 to the d thing, just maybe using its bit vector. From that, you have to compute the polynomial at that value, and then take the parity or one of the bits of the polynomial, and that is your final answer. Right? So each of the SK counters has to be updated. Each counter update requires an evaluation of a degree 4 polynomial over f2 to the d, taking time which is like order d, right? Maybe d square. No, so okay, d log d or some such thing. No, it's fine. Yeah, d is fine. It's modular arithmetic. No, wait, no. Yeah, okay. Order quality. I think, yeah, certainly d square you can do it. I know, but division also. There's no division. Yeah, so there's a.
We're talking about just polynomial evaluation, right? Of degree d.
Yeah. So degree 4, not degree d. That's important. So each element itself requires d bits to represent
Right.
each coefficient. Yeah. So degree 4. So this is fine. So but that is the crucial thing, d square. Crucial thing is that there is an sk times thing, right? So the update time is also like omega sk. Is also the update time guarantee is also only from sk times poly d arithmetic operations. So the memory footprint is small, but you're almost going and updating all the memory, right? All of the memory uh, on every. Right? Yeah, so you're also going and updating all the counters, and so you're almost touching all the memory at every update. Okay, and this sort of shows maybe it's 1090. So yeah, maybe I can show you right now. So let's see if I can do this. So this is some code I wrote at some point to just check how well or how badly this works. Okay, so let me show you how these things are implemented and how they look like. So this is not supposed to be an engineering uh, like yeah, a proper engineering implementation. So this would be laughable for that kind of work, but it still. Wait, what happened? Okay. Okay, so yeah, so this is not the interesting point. So it's firstly, how do you create the four-wise independent random variables? So this is using this very nice library called NTL, the number theory library, it's written by Victor Shu. It's so yes, firstly, yes, this thing is just initializing. So this function is just initializing one particular realization of f2. So I said that this is for one reason for which different irreducible polynomials are different, really, although the fields are isomorphic, and that is in sparsity. Because when you compute, you will go modulo these polynomials. So if they have fewer non-zero coefficients, these operations might take less time. So for example, this library tries to choose the sparsest irreducible polynomial it can find. Usually so there is a conjecture that you can find one of degree 3, like with just 3 non-zero coefficients, 3 to at most 5 non-zero coefficients. So it tries to just use one of those. So in our case, it will be using something with 3 or 5 at most. Okay. And then, of course, the things that we discussed already. So there is this polynomial. The polynomial is chosen randomly. So that's what the pseudo-randomness. So this random number generator does that. So what it does is that it just stores a random polynomial. So you can see independence equal to 4. So this is just a random polynomial of degree at most 3. So it just uses one less. So that's what this guy stores. And whenever it has to get a so firstly, how do you get from the polynomial to the bit? This is exactly doing parity, Varun was talking about. So you take the evaluation that you get in GF2E is the field, the F2 to the D. The element you get, you convert it into a polynomial in GF2X, which you can do because that's the representation. And then you look at its weight, which is just the number of non-zero coefficients. So that's the parity. And you return -1 if it's odd, and if it's even, and 1 if it's or the other way around. So that's what, and this get bit function just essentially is doing that. So it takes so what is this from int n? So when you see the nth element, from that you have to convert it into a field element, right? First, so I see one of the elements in the alphabet. It is represented by some number between 0 and d. I have to interpret it as a field element in f2 to the d, which I can because there are that many elements. So this is just some way of doing it. Basically, what it does, it just converts it into a polynomial and then converts it into an element of f2 using just the library functions. And then it evaluates the random polynomial it has that it chose just once in the very beginning. Yeah, so the random polynomial that it had that it chose once in the very beginning, and it just so wait my cursor. Yeah, so and here it just evaluates the random polynomial. The random polynomial is chosen just once in the very beginning. It's not updated every time. For every new element, you will call this get bit function. What it does is that it evaluate the polynomial at a field element obtained from the new symbol that you just saw in the string, and then it will just return the bit. So that's how the 4-wise independence works. So this max bits 30 is, I'm just assuming that they're only 2 to the 30, so 1 billion, roughly slightly more than a billion, so 100 crores different symbols in this possible symbols in this string. So this is how the 4-wise is. This is a short implementation because all the heavy lifting, all the arithmetic is being done by NTL. Right? So as you can see, a lot of things are constructing the irreducible polynomial. So this thing, for example, this is the most non-trivial step here. We have to actually find the irreducible polynomial. But actually, what the library does behind our backs is that for such small things, it actually just does a lookup. It has already a stored irreducible polynomial. Just use that, and it will sparse irreducible polynomial. The set seed is just to set a seed for the library for an, so don't worry about that. And then there are two things I can do, right? So I can do the exact one. So I mean, I can just do an exact computation. I can just have some kind of a hash map or a binary tree, balanced binary tree based map, where whenever I see an element, if I have never seen the element, I create a new entry for it in a table and add 1 to it. Otherwise, I've seen the element, that entry is already there, I just add 1 to whatever the number was there. So then I keep the full frequency table. At the very end, I just compute the F2 by just squaring each element and summing it up. Right? So that's the exact thing that I could do. Right? So this is what we were thumbing our noses at, right? By saying that, oh, this takes so much memory. In the worst case, it will be taking like 10 to the 9. So it's like so my computer, which is not, it's like I think maybe 4 GB or 8 GB RAM, it will be covering up so much of its RAM and so on. Right, 4 GB. It was 1 to the 10 to the 9 elements, so that's already like 4 bytes per integer. That's like 4 GB, half the RAM already gone for this. Okay, that is fine. And then you also have the AMS implementation. And that one, as you can see, so okay, so I've cheated a little bit by not using the guarantees that we had. So we have this tolerance. I have put the tolerance as 0.3. So I am happy to tolerate 30% error. Okay, and you see why. And I only do these 5 repetitions. So like this, the number of medians I take, I think, is 5. Or yeah, so the number of copies I have is 5. And so I'm just taking, instead of like that 16 over epsilon square, I'm just taking 2 over epsilon squared samples. Again, you see why I'm doing less than what the guarantees ask for. And then it's just an implementation of what we were doing. So you first make these. So this is what the thing is doing. So you have a generator. So how many times you're repeating and how many samples you take for each repetition. For each one of those, you remember, right? For each ij pair, we needed an RNG, right? We needed this generator for these vectors, which are supposed to be independent. So each element of this generator is independent. Each of these generators will generate a vector of 4. So each of these rep type times samples generators will output this vector of size max bits, that 30 thing, which will be 4 wise independent. And yeah, this is a C++ issue. And what you do now is, whenever you see an element, you have to go over all of them, all of the counters, and do exactly what I said. Right? I mean, you basically get the bit for that element and add it. This is exactly computing the yij's. Right, and when you're done with this, yeah, so you just take the average over all your counters, and you then take the median. So all of those things, so you sort them and you take the median. Okay, so it's just a implementation, and but the reason I wanted to show you is not because the code exists, because of what it does. So I hope I have everything installed. So let me just check that. And this generate function, it just generates. So what it does is that if I give it say 10,000, it will generate sorry, on a random tree. It will just generate 10,000. It will just generate 10,000. These numbers are getting cut, but it doesn't matter. It will just generate 10,000 random sequence, and if I round the same C, it will generate the same numbers. So that's just to check how on the same number these 2 different algorithms. So let's try something. And let me also do this in here. So as you can see, a lot of the CPU right now is being used by Zoom. That's fine. So yeah, so we'll see that. Okay, so generate doesn't take anything. You don't even see it in the process list. Maybe. Okay, I think yeah, too late to figure out a syntax. I should have done that earlier. Okay, so let's see. The exact algorithm, of course, will give me the exact number. So 10,000, there were no collisions. It was just doing this fine. So let me also do this with the time. So yeah, it didn't take anything, like 0.023 seconds, and it gave me something. So 10,000 is not going to work. AMS also would do. See, okay, so you already see some problem, right? It took much longer, but it gave a decent answer. Like I wanted 30% error, but it is giving me like 7% error, I think. Okay, so fine, but this is going to get worse. So I increase by the number of, so increase the number of elements by 10, and I look at exact. Okay, 0.15, and now I look at AMS, and it will take I think longer. But you notice that the memory is 0.01%. It's taking a lot of CPU, but the memory requirement is okay. So you just remember that it was something like 0.1%. Okay, and it gave a decent estimate, 20% off. But okay, my tolerance was anyway 30%. There was not even following the guarantees. But okay, let me now increase it by a factor of 100, and so now you see that the exact should see some memory footprint. So you can see that the memory is already like quite high, but it is running quickly enough. Okay, so it's like 5% memory. So that is like something like 400 MB, but it gave the correct answer. AMS, if you let it run for long enough, it will give you some decent estimate. Its memory will not go beyond 0.01, but it will take forever. And the reason it takes forever is something we already discussed. Is the fact that it has to go and touch every bit of the memory it's using at every single update. The exact one is basically it's either a hash table or a balanced binary tree. It takes log and update time. So its memory usage keeps increasing, but its time is quite fast, especially because all the data structure is still in memory. So this was just to show that so we had a nice theoretical guarantee, but even a theoretical guarantee was telling us that something can go wrong if you just use it right like this in practice, because each update step you're going to have to touch all the memory. So so one place where it would be very nice if I had some kind of a massively parallel machine like a GPU, so then I could have this counter on completely parallel, right? So I can do this in completely in parallel, right? So I get an element, each of these counters doesn't have to talk to any of the other counters until at the very end when I have to take averages and so on. But that is a fast operation. While this stream is running, these counters are on their own, like they can be on completely different machines. So their AMS would run very fast because it's just each single counter update is not that bad, but so many counter updates is bad. And as you can see, it has not even finished 1/10 of the job yet. And but the good thing is that its memory usage is not, and it will not rise if you trust me. The code is there on a web page on the previous class, and you can run it and convince that the memory usage does not change, because you must have seen that the code only does one memory allocation in the very beginning. It just initializes the counters and the random number generators, and then it doesn't use any more memory. So the memory is just assigned upfront and never changes. The exact one has to keep assigning new memory, because as it sees newer and newer entries, it has to keep adding. Okay, so that was just some demonstration of engineering incompetence on my part. But okay, so that's but it also has some lesson that so you have to look carefully at a theory bound. You have to look at all the terms, not just the log d term, but also the 1 over epsilon square term. That is in fact what is causing havoc here. That's why I had to make it 2 over epsilon square, not 16 over epsilon squared, and that's why I had to choose a tolerance of 30% and not 1%. Because if you choose 1%, it's like 10,000, a factor of 10,000 right there, right? Because 1% is like 1 e minus 2. Square of that is 1 e minus 4, and you're picking the inverse of it. So this 1 over epsilon squared that comes very often in these things is a pretty bad thing, and a lot of work is devoted to usually to try to get rid of this 1 over epsilon square, make it smaller, like even 1 over epsilon and so on. So so in a particular application, different factors that you get out of this of a theoretical analysis might be the sort of the guiding. Oh good, it has covered 10%. Is memory usage has not increased by much. If you remember, exact at this point was already about 10 times the memory. But okay, that's what it is. So I'll just stop torturing my CPU and. Okay, so so any questions on this?
So right now, what we've done is we have been able to estimate F2.
Yeah.
I mean, and what was that? But we have we solved the, like, what was that heavy hitter
There's no,
thing?
I said, so there's no formalization of the heavy hitter problem. This is one formulation that you just estimate F2. If F2 becomes too large, then you say there is some heavy hitting happening. One other formulation is you keep track of all. So yeah, so this is an exercise you can try. It's interesting. I think it's called grease mist or something. So you can, so you want to keep track of all the top k elements, or rather not all the top k elements, that will be hard. Well, you want to keep track of all elements. So you have a number k, and so let's say k equal to 2. You want to keep track of any element that has hit more than n by k times, so n by 2 times. And this you can do in small memory. So that's an interesting thing that you can try. So that's another formulation of the heavy hitter problem. There are other versions of it. Like, so basically, yeah, because this one gives you something. It's interesting also because it relates to something called Johnson-Lindner-Strauss embeddings, which you'll see later, somewhat similar in spirit. But this particular formulation, as we saw in this application, doesn't seem to work nicely because of, at least on a single CPU kind of system, unless you have more code. So you might use, so in an application of heavy hitter, you might just change the formulation. So if you are running with some resources like my desktop, which doesn't have just maybe 3 or 4 cores or 2 cores, you just don't use this, and you try to use the Mishra grease kind of thing. And so you're solving a different problem then, but the application problem is different. It's just finding heavy hitter in some way. So the formalization that you use is a figure of merit is finally in how good it is at detecting those heavy hitters that were somehow affecting your system badly. One option could be is an F2 computation checking that F2 is too large, so that you detect that something is wrong. Yeah, and the other could be just checking if something is just really high, n by 2 or something.
Also, so for the guarantees that we got for space, like for our given error and tolerance and stuff, is there a lower bound?
Yeah, so I don't remember. We should check the AMS paper. I think so. Yeah, I think even for randomized, this is more or less possibly tight for this problem, but I don't remember the full details. So I don't know which terms are tight and which are not. So. Any more questions?
So that's not from the AMS paper, but the lower bounds are not from AMS, but you can use communication complexity to show that many of these
had the same communication complexity lower bounds also, right? Maybe only for data.
Oh, possibly not. So, okay. So you are just computing F0. You can compute every single F0, F1, F2, F3. I think everything was shown to be tight in subsequent papers.
Oh, so I think they also had basically one-sided communication complexity lower bounds. Let me just look at that.
Yeah. So for one of them they have, but I think the full thing you need it happened a few years later.
Yeah, this is Jairam and others. Right?
Yeah.
Using this essentially like the Shearer chain rule.
So this kind of getting low memory footprint is it's only possible with some FK, right? Not possible for
what?
No, for every FK they have a bound, and
we have a bound, and we have, in fact, I think we have matching upper and lower bounds for every FK.
But for every FK, is there some really low memory footprint stuff that you can do? Or?
No. Higher memory, I think higher FKs you get.
Memory increases more. Yes, F2 is the best in that sense. I think you get worse for F3, F4, etc.
So there the trivial stuff is the best stuff, is it?
Not the trivial. You can do better than the trivial.
It's there in the same paper. It's
right.
better, but it's not. Yeah. It's using a slightly different idea. So here there are a lot of nice things happening. The fact that variance, so essentially that the variance forms some kind of a norm on random variables, and independence sort of corresponds to, or rather covariance forms some kind of inner product over random variables, and independence is sort of the orthogonality relation for that. So that is the interesting thing that let us do a lot of nice things here. that is not there for other cases.
So for the AMS sketch paper, is the paper itself the best resource to be read, or is something?
It's a well-written paper. It's a bit, I think it's a good paper to read in the sense that there'll be a lot of things that they write as if it's obvious, and then you have to think about it. So it's good in that sense.
So just to answer Varun's question, so for fk, for k greater than 2, you can do it in n. The trivial is in space n, but you can do it in n to the 1 minus 1 over k.
Yeah, so there's an n factor that comes in. So it's the k times log. So the exact expression that they have is k times log 1 over epsilon. So k times log 1 over delta. In our notation, it will be k times log 1 over delta by epsilon squared times n to the 1 minus 1 over k. So notice that if you put k equal to 2, you will get a square root n. N is the number of like the n is the so n here is d. So d times, so you will get a square root d factor in front if you use their fk algorithm for k equal to 2. So they get rid of the square root d dependence.
And for all k greater than 2, you can show that what the expression you just said is right.
So for F0, you will do it in the homework, which there's another very nice method that it's there in the in the homework. So you should.
Yeah, for those attending the communication complexity course, the lower bound might be covered there.
Yeah, or at least the communication complexity is needed for it. Yeah.
For doing that.
Another place to look at it is the Teamer of Garden has some notes, but I was looking at them yesterday and there are some bugs, but they're nicely written. So you have to be careful reading it. These are written in a hurry or something, but they give a nice overview of what is like why communication complexity comes in, why would you thought of it, and so on. It's called communication complexity for algorithm designers. So you can look it up. Okay, so that was for AMS and the design of AMS. So yes, so maybe like this, I don't know, moral lesson, whatever, from looking at the code. Yeah, yes, so one thing is that even the theoretical bound warns about a bad dependence on 1 over epsilon squared on the update time per item, unless counters apply. And implementations, implementations have to be careful. So what I did was just use generic things, but you can potentially, and this is done in coding theory, so the construction that we're using is very similar to many error correcting codes, and people have worked for decades on making them efficient, like sometimes even on chip, like not just in the algorithm, but even designing chips so that the kind of field computations that are needed can be done fast. So implementations matter. So a generic NTL based, although NTL is quite well optimized as far as I know, but it's still like a properly optimized implementation could do much better. Possibly do much better. Constants hiding here could be reduced by a lot, and that matters in this setting because it's hitting you for each update. Okay, so that would be all for AMS. There's 15 minutes left, and unless there are any questions, there's one thing that I forgot to do last time, which was give the proof of the hoping bound for the bounded case. So I wanted to do that. So unless there are questions, I'll just, that will be the final thing for today. Okay, so if not, so okay, so let's just do this. So what is the thing we want to prove? So we use this already in the proof. So let me just recall what it was. So use this but never proved. So theorem is that let x be a. So I'll just assume mean 0. If it's not mean 0, you can just subtract the expectation and fine. Let x be a mean 0 random variable. Taking values. Okay. So of course, I mean, we won't use it, but this implies that A has to be, I mean, on one side of 0, B has to be another side of 0. And then, what was the expression we're using? Phi, right? Phi x lambda defined to be log of E of x for lambda x satisfies. Phi x lambda is less than b minus a squared. Wait. Yeah. So this proof that I'm going to give is might look somewhat mysterious, but it's not quite. Actually, it's in some sense the more analytic one. It uses the fact that it uses the fact that the moment generating function is really the generating function of the moments, right? So in some sense it might be the more. So if there's time, I'll give the other one also. But let's just do this one first. So what I will do is the following. So we'll go completely analytically. So what is phi x of 0? Yeah, what is phi x of 0?
0.
It's a 0.
Yeah, it's 0 because it's log of 1, right? So e to the power 0x is just 1, so expectation of 1 is 1. Okay. What is phi x derivative with respect to lambda of at any particular lambda? So let's just do this derivative. Okay, so I'm assuming that. So assuming, but not really assuming, because all this is fine here. So assuming assuming major theoretic conditions for integrating under the for differentiating under the integral. But all those are satisfied. I'm just not writing condition for differentiating. But you have to be more careful if the variables are not bounded. So so it's log, so you will get the thing here. And then you have to differentiate the expectation. So the derivative just goes inside the thing, and you get e x times x lambda x. So crucial thing is that so there's a point is an x here. then this in fact is sort of like the first. Yeah, so that one thing to note, that this is already, it's looking like some different expectation of x. And what is a different expectation? It's under a different, so why can I write it as an expectation? It's under a different measure, different probability distribution. What is the probability distribution? It reweights the original probability distribution by discretely lambda x weight. So what do I mean by that? So what this means? So let me call this E. So E mu lambda. Okay. So what is this mu lambda? So let me define this probability distribution. So we define. So right now I'm just defining this, and then I'll show that is a proper estimation. We define E mu lambda of any random variable z to be E, the original expectation, times z times x of lambda x divided by E of x of lambda x. Okay. And this is a probability distribution. This is a probability distribution because, so this is a positive measure and it's a probability distribution. So this is a probability distribution because so mu lambda is a probability distribution. Because E mu lambda of 1 is just 1. You just check by putting the equal to. Okay, so this is just to keep in mind. But coming back to our thing, we also know that yx prime of 0 is the expectation of x divided by just 1, which is 0, because x was 0. So phi is 0 at 0, and its derivative is also 0 at 0. Okay, those are two things we have so far shown. So now we look at a second derivative. So we just differentiate this expression, right? So what does it become? So it becomes E of x of lambda x squared, and now I have to differentiate that here. So it is E, or let me just do it like two steps. So if I do it like this, like E x squared x lambda x minus, and the other one is where I have to differentiate the thing in the denominator, and then it just becomes okay. This is just calculus, right? Standard stuff. But notice something. What is this? If I write it like this in the previous notation, this is E mu lambda of x squared minus E mu of x squared, E mu lambda of x squared. Okay, which is just the variance under mu lambda of x. So far everything is fine, right? No problems. But what can the variance of x be? X is a bounded random variable. No matter what probability distribution I put on it, its values are between a and b. So what can its variance be?
It can be at most b minus a the whole square by 4.
Yeah, so it can be at most that, and one way of seeing this is the following. So so it's clear that it should be at most like b minus a squared, right? Like, because the mean is something between b minus a, like, so the variance is also, I mean, it also has the following representation, right? So both numbers are between a and b. Okay? The mean also has to be between a and b because x is between a and b. So clearly less than b minus a squared. But actually, you can do better, and the reason is that you don't have to do it. So the point is that this is also equal to the minimum over all t in the real numbers, in fact, of e mu lambda x minus t squared. So this you can show easily. The variance is the minimum squared deviation from any point. The minimum is achieved at the mean. So I just use t to be equal to the midpoint, right? So in particular, this is less than e mu lambda x minus b minus a by b plus a by 2. But the maximum distance from the midpoint of any point in the interval is at most half the size of the interval. So this is less than and that is just okay. So what do we have so far? So we have that phi x of 0 is phi x of 0 is equal to 0, phi x prime of 0 is equal to 0, and phi x double prime of any lambda is less than b minus a squared by 4. And this completes the proof, because now you use the Taylor's theorem with the remainder on the second order. So by the second order remainder, because phi is differentiable everywhere on all lambda, second order lambda, second order term, we have phi x of lambda is equal to phi x of 0. We have that for every lambda in R, there exists mu in R, such that in fact the mu has to lie on the line segment joining 0 and lambda, but I don't even need that right now. Mu on segment 0 to lambda plus phi x prime of 0 times lambda plus phi x double prime of 0 of mu lambda squared by 2. So we don't know what mu is, but we know that so we know that this is equal. This term is 0. This term is 0, and this term. So this is actually equal to, for us, phi x double prime mu lambda squared by 2. But this we know is less than b minus a squared by 2. Okay, so that finishes the proof. Yes, so this I think is Hovding's original proof. I mean, it just highlights that you can use the analytic properties of the cumulant generating function also quite nicely. The other proof is basically just linearizing it. So use the fact that exponential of lambda x is a convex function, and hence it's dominated by the convex combination of its values at the endpoints. So then it becomes just a 2-point problem for a linear function, and if you do that way, I think you will get 4 here instead of 8. That's another way of doing it. Yeah, so because it's already 11, I will probably maybe not do that. So all you have to do is to just use the fact that x lambda x for any x between a and b, because x is a convex combination of a and b because it has to lie between a and b. So e to the lambda x for any lambda is a convex function of x, and therefore it can be linearized in terms of its values at a and its value at b, and that gives an upper bound on this. And now you take that log of expectation of a linear function, and that you can just optimize using simple calculus. Okay, so that was all. Next time, I think we'll start some maybe linear programming and duality in general. So